Hi all, welcome to the second part of the lecture on heat exchangers. In the first part, we have discussed about various classification of heat exchangers, and then we discussed the important parameters for the analysis of heat exchanger, like surface area of heat exchanger, the importance of overall heat transfer coefficient, and also the significance of LMTD, that is logarithmic mean temperature difference. Okay. So this part of the lecture mainly focused on the two important methods commonly used to analyze a heat exchanger. First one is the LMTD method, and the other one is the effectiveness NTU method. Let's discuss LMTD method first. Okay. Here you can see temperature profile for both parallel flow and counter flow heat exchangers. So we know in a parallel flow heat exchanger, both fluids moves in the same direction in the heat exchanger. Okay. So here the suffix H represents the hot fluid and C represents the cold fluids. And the suffix 1 represents the inlet condition, the suffix 2 represents the outlet condition. Okay. Suffix 1 represents inlet condition of the heat exchanger and suffix 2 represents the exit condition of the heat exchanger. Okay. So you can see the hot fluid in a parallel flow heat exchanger and counter flow heat exchanger loses its heats from inlet to outlet, and the cold fluid gains heats from inlet to outlet. In case of counter flow heat exchanger, it moves in the opposite direction of cold fluid. Okay, cold fluid moves from this side to this side, and the cold fluid moves in the opposite direction. So this is the inlet of the cold fluid in a counter flow heat exchanger, and it gains heat during this movement and its temperature increases. Okay. Here the important thing we should note that the temperature difference at inlet we represent with the letter eta 1, and okay, so it is also represented in some textbooks as delta T1. Delta T1 equal to theta 1. Okay, so in a parallel flow heat exchanger, delta T1 or theta 1 is the difference between EH1 minus EC1. Okay. But in case of counter flow heat exchanger, theta 1 is EH1 minus EC2. This is theta 1. So in counter flow heat exchanger, this is the inlet temperature of hot fluid, this is the outlet temperature of cold fluid. Theta 1 represents EH1 minus EC2 in case of counter flow, but in case of parallel flow, it is EH1 minus EC1. Okay. And at the outside, theta 2 represents, in case of counter flow heat exchanger, theta 2 is EH2 minus EC1, but in case of parallel flow heat exchanger, it is EH2 minus EC2. Okay. So we are going to consider a elementary area on the texture, and we will apply energy balance equation. Okay, so let's move on to parallel flow heat exchanger first. So this is a parallel flow heat exchanger. Hot fluid enter at this side and moves out from the heat exchanger this side. Okay. In the same way, the cold fluid also enter to the heat exchanger at this side and moves exit at this side. Okay. The inlet temperature of hot fluid is pH1. Inlet temperature of cold fluid is PC1. Difference between pH1 and PC1 is theta1. pH1 is PC1. And the exit temperature is pH2 and PC2, and its difference is denoted with theta2. Okay, so in a parallel flow heat exchanger, the energy balance equation, or if we apply the first law of thermodynamics here, we get for hot fluid is heat given up by the hot fluid. Q is equal to mH Cph pH1 minus pH1 minus pH2, because pH1 is higher than pH2. Okay. Heat picked up by the cold fluid, Q is equal to, both these quantities are same. Okay. Q is equal to mc Cpc PC2 minus PC1 here, because PC2 is higher than that of PC1 in case of cold fluid, because the temperature of the cold fluid is increases from inlet to outlet. Okay. The total heat transfer rate in a heat exchanger is given in this equation. Q is equal to UA theta m, where theta m is the LMTD. Importance of LMTD we already discussed in the first part. Okay, and also in the case of overall heat transfer coefficients. Okay, so let me define LMTD again. LMTD or theta m is defined as a temperature difference which, if constant, would give the same rate of heat transfer as actually occurs under variable condition of temperature difference. Actually, in actual practice, the temperature difference, cold fluid and hot fluid, from inlet to outlet is varying continuously. But if we consider a constant temperature difference from throughout the heat exchanger, it will give the same heat transfer rate from the heat exchanger. That temperature difference is called LMTD. It's a constant temperature difference throughout the heat exchanger, which gives the same rate of heat transfer as actually occurs at varying conditions of temperature. Okay. So we are taking some assumptions for the derivation of LMTD. The first assumption is the overall heat transfer coefficient U is constant throughout the exchanger. And we consider the steady state condition. That means the temperature is not varying time. Okay. Then the specific heats and mass flow rates of both fluids are constant throughout. The heat exchanger perfectly insulated. That means there is no heat loss to the surroundings. The other assumption is there is no phase change. There is no phase change for both fluids. Then the other assumption is the potential energy and kinetic energies changes are negligible throughout the exchanger. And there is no axial heat conduction around fluids in the exchanger. These are the assumptions. Okay. let's take a elementary area dA on the heat exchanger. Okay, this is the temperature profile for a parallel flow heat exchanger or fluid. The temperature is pH1, the temperature is pH2, which will decrease from pH1 to pH2 around the area of the heat exchanger, and the cold fluid gains heat from inlet to outlet. Tc1 is the inlet temperature and Tc2 is the outlet temperature. Theta1 is the difference in temperature. H1 minus Tc1, H2 minus Tc2 is Theta2. Okay. The inlet condition denoted with letter 1 and outlet condition denoted with letter 2. Okay. And the area from inlet to outlet is increasing from 0 to the total area of the lake. Okay. Now consider an elementary area dA of heat exchanger. Okay. So through this elementary area, the temperature, the heat transfer rate, the rate of heat transfer is dQ. That is equal to U dA pH minus Pc, where pH and Pc is the temperatures of hot fluid and cold fluid on the elementary area. Okay, so pH minus Pc is represented as theta. Okay, as a result of this heat transfer dQ through the elementary area dA, the hot fluid is cooled by an amount dTH, and the cold fluid is heated up by an amount dTc. So we can write the equations. We apply the energy balance here, or we apply the first law of transfer here. We can write dQ is equal to minus mHCpH dTH. mCp. Okay, dTH is the amount of temperature difference on this area here. Okay, in case of hot fluid. Here, this minus sign represents, actually, it loses its heat. Okay, so energy loss or heat loss from a system is represented as negative. Okay, this is negative, but in case of cold fluid, the quantity is positive because the system is gain heat. Okay, so that is mCp and Pc. That should be equal to U dA pH minus Pc. pH minus Pc. It's the temperature difference on this area. Okay. So from this equation you can write the temperature difference dTH for hot fluid, that is minus dQ by mHCpH, that is equal to minus dQ by CH. So this quantity mHCpH we represent with a single term CH. Okay, and also from this equation you can write dTc equal to dQ by mCpC, that is equal to dQ by Cc. Okay, so now perform the operation dTH minus dTc. dTH minus dTc, that is equal to minus dQ by CH minus dQ by Cc. So take this quantity dQ outside the bracket, so minus dQ multiplied with 1 by CH plus 1 by Cc. Okay, so we know dH minus Pc is theta, so we can write dH minus dTc is d theta. Okay, d theta is equal to minus dQ multiplied with 1 by CH plus 1 by Cc. Now let's substitute the value of dQ from the the equation dq is equal to UVA TH minus TC. Okay, so we will get d theta is equal to minus UVA TH minus TC 1 by 6% by 6C, where TH minus TC is theta. So substitute that value here and rearrange the equation. Okay, here d theta by theta is one variable, varying parameter, and another varying parameter is dA, that is area from inlet to outlet. So to get the total heat transfer rate, integrate this equation from inlet to outlet. Okay, the area is varying from 0 to capital A. Capital A is the total area of the heat exchanger. Okay. Now, so here apply the limits. 1, 2 is inlet to outlet. D theta by theta, that's equal to minus 1 by CH and 1 by CC is constant and U is also constant. So take it outside integration. Okay, so and apply the limit here. It is area A is equal to 0 to capital A. Okay, so you'll get on left hand side you will get ln of theta 2 by theta 1 is the temperature difference exit at inlet. Okay, theta is the temperature difference at exit of the heat exchanger, and theta 1 is the temperature difference at the inlet of the heat exchanger. Okay, so that is equal to minus UA 1 by CH plus 1 by CC. Put this equation as 2. Now, total heat transfer rate between two fluids is, we can write Q is equal to CH, that is MHCPH for hot fluid, multiplied with pH1 minus pH2, that is the temperature difference of hot fluid inlet temperature and outlet temperature. pH1 minus pH2 is the total heat transfer rate, total heat loss from the hot fluid. That is equal to the temperature. That is equal to the heat gained by the cold fluid, that is MCCPC, that is CC, multiplied with the temperature difference TC2 minus TC1, because TC2 is higher than that of TC1 here. Okay, because the cold fluid gets heat from the hot fluid, so the TC2 is always higher than exit temperature of cold fluid, always higher than that of its cold fluid, its inlet temperature. Okay. From this equation, find the equation for 1 by CH by CC. 1 by CH by CC. 1 by CH is equal to pH1 minus pH2 divided by Q. Okay, and 1 by CC is TC2 minus TC by Q. Substitute these two values of 1 by CH and 1 by CC in this equation 2 and rearrange the equation to get the transfer equation. We substitute these values in this equation. We will get ln of theta by theta 1 that is UA 1 by CH. In place of 1 by CH, substitute pH1 minus pH2 by Q plus TC2 minus TC by Q. Take this value outside and this negative sign inside of the bracket and rearrange the equation. You will get UA by Q multiplied with pH2 is positive here because P multiplied is minus sign in the bracket. pH2 is positive, so pH2 minus 3 is equal to TC2 is negative, Okay, so pH2 minus TC2 minus of pH1. pH1 negative quantities minus pH1 and TC1 is will be positive here, so minus of minus will be positive. Okay. So TH1 is this one. So arrange the terms within the bracket such that we get the inlet temperature difference and outlet temperature difference in the texture. Okay, so theta 2 is the temperature difference, exit temperature difference in hot and cold fluid. Theta 1 is the inlet temperature difference between hot and cold fluid. Okay, so Q is equal to UA theta 2 minus theta 1 divided by ln of theta 2 by theta 1. This term theta 2 minus theta 1 divided by ln of theta 2 by theta 1 is represented with a single term which is called theta m and is known as LMTD. Okay, theta m is LMTD for a barrel flow heat exchanger. So LMTD for a barrel flow heat exchanger is theta 2 minus theta 1 divided by ln of theta 2 by theta 1, where theta 2 is TH2 minus TC2 and theta 1 is TC1 so TH1 minus TC1. Okay, it's called a logarithmic mean temperature difference for a barrel flow heat exchanger. So here the equation UA theta m for heat transfer rate. Okay. Now let's take the counterflow heat exchanger. We have the equation Q. Okay, let's take an elementary area QA from the heat exchanger and the temperature difference of that area is theta H minus DC. Okay, the heat transfer rate to the elementary area is Q, that will be equal to U dA TH minus DC. So due to the heat transfer to the area dA, the hot fluid cooled by an amount dTH and dTH, and the hot cold fluid heated up by an amount dTC. The important thing noted here is the temperature difference at the left end of the exchanger. Okay, one end of the exchanger is TH1 minus TC2 is represented theta 1 and TH2 minus TC1 is represented theta 2 because the cold fluid is moving from this end to this end and the hot fluid moving from the opposite direction, this end to this end. Okay, so keep this in mind. Okay, both fluids are moving in the opposite direction in a counterflow heat exchanger. Okay, so we can write the equation by applying the energy balance first of thermodynamics. dQ is equal to minus mc CTH, that is equal to minus mc CTC. In this case, here also, in case of cold fluid also, we have a minus sign because the area is increasing. We are taking from this side, area is increasing. Okay, but the cold fluid is moving in the opposite direction, that's why minus sign here. Okay, this minus sign represents the heat loss from the cold fluid. Okay, so in both the time you get minus sign in case of counterflow heat exchanger. That should be equal to UA, which minus. Okay, this is equation number 1. Now from this equation, find out the pH is equal to minus A2 by MSCH, represented with minus A2 by CH. Okay, ATC is equal to minus A2 by CC. Now perform the operation pH minus BC is equal to minus 2Q 1 by CH minus 1 by 60. In case of parallel flow heat exchanger, this is positive 1. But here it is negative because both these terms are okay. So minus dq into 1 by ch minus 1 by cc. So dth minus dtc, you can write d theta because dth minus dc is theta. So theta is equal to Now substitute the values of 1 by ch and 1 by cc in the equation. Substitute the value of dq from the equation number 1, UA h minus dc. Okay, UDA. This equation is UDA h minus dc. Correct. Okay, so minus UDA h minus dc into 1 by ch minus 1 by cc. Okay. Now rearrange the equation and integrate. Okay, d theta by theta minus u dA 1 by ch minus 1 by cc, and integrate the limits to inlet to outlet and area equal to capital A. So we will get ln of theta 2 by theta 1 is equal to minus 1 by cc plus 1. Now substitute for 1 by ch and 1 by cc from the total heat transfer equation for both fluids is equal to ch1 minus ch2 is of hot fluid, that is to cc ec2 minus ec1, ec2 minus ec1 is of cold fluid. 1 by c is equal to ch1 minus ec2 is equal to 2, 1 by cc is equal to ec2 minus ec2. Substitute these two values in this equation. Get and rearrange. Get here ln of theta 2 by theta 1 is equal to minus ua ph1 minus ph2 by 2. Take q outside and rearrange within the bracket ph1 minus pc2, that is theta 1. Okay, arrange by considering this temperature graph, temperature profile. Okay, theta 1 and theta 2. We will get theta 1 and theta 2 within the bracket. Okay, so ph1 minus pc2 is theta 1. Arrange that ph1 minus pc2. pc2 is minus here. Minus of ph2. ph2 is minus and pc1 is a positive quantity. So minus of ph2 minus pc1. So that theta 1 is theta. And take this minus sign within the bracket. So you will get ua by q theta 2 minus theta 1. So rearrange the equation. Q is equal to ua theta 2 minus theta 1 from the ln of theta 2 theta 1, that is equal to ua theta m, where theta m is LMTD for counterflow heat exchanger. So you will get the same equation as in case of parallel flow heat exchanger, but the quantities theta 1 and theta 2 is different here. Okay, so for both parallel flow and counterflow heat exchanger, LMTD is denoted with theta m, or you can use the letter delta TLM. It's equal to theta 1 minus theta 2 divided by ln of theta 1 by theta 2, or you can write either another way, theta 2 minus theta 1 divided by ln of theta 2 by theta 1, or you can use the letter delta T1 and delta T in place of theta 1 and theta 2. Okay, so the total heat transfer rate is UAS. AS is surface area. Okay, total heat transfer area of the cylinder multiplied with LMTD delta TLM. Okay, so in a counterflow heat exchanger, The temperature difference between the hot and cold fluid will remain constant along the heat exchanger when the heat capacity rates, that is MCP value of both fluids are equal. See here, MHCpH, if MHCpH is equal to MCCpC, then both case delta T 1 equal to delta T2. Okay, delta T1 equal to delta T2. Okay, so that case, in case of counterflow heat exchanger, you will get 0 by 0, that is indeterminate. By applying hospital rule, then delta T1 is equal to delta T2 is equal to delta T LM. So this is only in case of counterflow heat exchanger. In case of parallel flow heat exchanger, delta T1 never equal to delta T. The LMTD for a counterflow heat exchanger is always greater than that of a parallel flow heat exchanger for a specified inlet and outlet temperatures. You can calculate it by applying some values. Okay. Always counterflow heat exchanger LMTD is higher than that of parallel flow heat exchanger LMTD. So, for a specified heat transfer rate, a counterflow heat exchanger is having lesser size than of a parallel flow heat exchanger, or a counterflow heat exchanger need lesser area for a particular heat transfer rate. Okay. So you can found LMTD correlations for counterflow, parallel flow, and also for crossflow heat exchangers from the data book page number 160. Okay. Now let's take the cases of multipass shell and tube heat exchanger or a crossflow. Okay. In case of crossflow or multipass shell and tube heat exchanger, the LMTD expressions are too complicated because of the complex flow conditions. Okay. In that case, we use a correction factor to calculate the LMTD in these cases. Okay. So actually we use a correction factor with the LMTD relation for a counterflow heat exchanger in a counterflow heat exchanger. So delta T LM, that is LMTD for multipass and crossflow heat exchangers, is equal to a correction factor multiplied with delta T LM for a counterflow heat exchanger. We know the counterflow heat exchanger LMTD is delta T1 minus delta T2 divided by ln of delta T1 minus by delta T2, theta 1 minus theta 2 divided by ln of theta 1 by theta 2. Okay. The counterflow heat exchanger delta T1 is, or theta 1 is Th1 minus Tc2, Th1 minus Tc2, and theta 2 is Th2 minus Tc1, Okay. So we use a correction factor to find the LMTD for multi-pass and crossflow heat exchangers. Okay. So for a multi-pass and crossflow heat exchanger, your heat transfer equation Q is equal to U A F delta T LM counterflow heat exchanger. Okay. Refer data with page number 167 to 167 for charts correction factors. Okay. These are some typical charts for correction factors. Okay. these correction factors actually you can find by using two dimensionless temperature terms, namely T and R. Okay, so all these charts you can see T is equal to a ratio, temperature ratio, small t2 minus small t1 capital T1 minus small t1, where capital 1 and 2 represents the inlet and outlet conditions. You can see here in this figure. T1 is the tube side, small t1 is a tube side fluid inlet temperature. The small t2 is the tube side fluid outlet temperature. The capital T1 is represent of shell side. Okay. So capital T1 is the inlet temperature of shell side fluid and capital T is the outlet temperature of shell side fluid. Okay. So this is the ratio T2 minus T1 to the capital T1. Okay. And the other dimensionless temperature terms represented with capital R, which is capital T1 minus capital T2. That's the temperature difference in shell side fluid, and small t2 minus small t1, that is the temperature difference in the tube side fluid, tube side. Okay. Capital T represents shell side and small t represents tube side. Okay. So we know that MCT, capital T1 minus capital T is a shell side heat transfer rate, and MCT small t2 minus small t1 is the tube side heat transfer rate. Okay, tube side heat transfer rate. Okay, so we can say that capital R is the capacity ratios. Capacity ratio, tube side and shell side. So the value T ranges from 0 to 1 because always the denominator T1 minus capital T1 minus small t1 is the maximum temperature difference available in the system. Capital T1 is the inlet temperature of the shell side fluid, small t1 is the inlet temperature of the tube side fluid. So this is the maximum available temperature difference heat exchanger. Okay. So the denominator is always higher than the numerator in this expression. So the value of T always ranges from 0 to 1. Okay. The value of R ranges from 0 to infinity. We can clear it from this expression. Okay. If this will happen when in case of phase change process, that is in case of a condenser or a boiler or evaporator, one fluid getting phase change. Okay, so if the fluid on the shell side experience phase change, then its temperature will not change. That is T1 is equal to 0. Okay, so R is equal to 0 corresponding to the phase change on shell side, and R is equal to infinity corresponding to the phase change on tube side. If the tube side fluid experience phase change, then this denominator will be 0, so it will be the value of R will be. So in case of condensers and boilers or evaporators, take the value of correction factor is always 1. Okay, these charts you can found from the data book, page number 167 to 170. Now The next method, the second method for the analysis of heat exchanger is the effectiveness method. This method is used when both the outlet temperatures of hot fluid and cold fluid are unknown. If the outlet temperatures of both fluids are unknown, we can't or we couldn't calculate the LMTD. Okay. So in that case, we are using the effectiveness method. This method is based on a dimensionless parameter called the heat transfer effectiveness, which is defined as the ratio of actual heat transfer rate to the maximum possible heat transfer rate. Okay. Actual heat transfer rate we can calculate by taking any of the fluid. If you take cold fluid, this is the actual heat transfer rate. MCCTC, TC out minus TC in. Okay, TC out is always higher than TC in. So TC out minus TC in. MCCTC is denoted with CC. Okay, that should be equal to, if you take the hot fluid, then MHCH, that is CH, multiplied with the temperature difference, pH in minus pH out. pH in is always hot fluid inlet temperature is always higher than that of hot fluid outlet temperature. Okay, so this, by using this equation, you will get actual heat transfer rate. Now, if Cc is not equal to Ch, if Cc not equal to Ch, the fluid with the smaller heat capacity rates, means Cc or Ch, smaller heat capacity rate will experience larger temperature change. You can see from this equation, if Ch is less than that of if Cc is less than that of Ch, then the quantity Tc out minus Tc in is higher than that of this time, right? So in the other case, if Ch is less than that of Cc, that is Ch is minimum that of Cc, then this time will be higher than that of this time. So it is clear that the fluid with smaller heat capacity rate will experience larger temperature change. Now, to get a maximum possible heat transfer rate, Qmax, this Qmax occurs when fluid of small heat capacity rate, fluid of small heat capacity rate undergoes maximum temperature difference available in a heat exchanger. Maximum temperature difference available. What is the maximum temperature difference available in a heat exchanger? That is pH in minus Tc in. Right? Just refer this figure, the temperature difference. Okay, temperature profile in a counterflow heat exchanger. pH1 minus Tc1 is the maximum temperature difference available here. Right? pH1 is the maximum temperature, Tc1 is the minimum temperature in a heat exchanger. So pH1 minus Tc1 is the maximum temperature difference available in a heat exchanger. Okay. In case of parallel flow also, you can notice that. See, pH1 minus Tc1, the maximum temperature difference available in a heat exchanger. Okay, that is parallel flow or counter flow. So you can get the maximum heat transfer by using this equation, that is Qmax is equal to C minimum, either of these two values which is minimum, okay, that is C minimum, multiplied with maximum available temperature difference, that is pH in minus Tc. So this is the equation for Qmax. Okay, so you can write effectiveness equation equal to, we consider the hot fluid MHCpH H1 minus pH2, that is the actual heat transfer rate divided by maximum possible heat transfer rate, that C minimum multiplied with H1 minus Pc1. C minimum is the lowest value of Cph and CH and Cc. Lowest value of CH and Cc, that is C minimum. Okay, so MSCpH we can write CH. Okay, so this equation. To consider the cold fluid, you can write Cc Tc2 minus Tc1 divided by C minimum pH of Tc. This value is common for both equation. Okay, both this equation, this is same. C minimum to H1 minus Tc. There is a maximum possible answer available possible in a heat exchanger. So effectiveness is equal to QH divided by Q max. So Q actual, use this equation, get Q actual, the effectiveness multiplied with maximum heat transfer, that is C minimum to H1 minus H1. C minimum is either MHCpH or MCCpH, which is minimum. Now NTU, other term, effectiveness NTU method. Other term NTU is another dimensionless parameter, which is the measure of the size of the heat exchanger. Actually, you can see that this is the equation for NTU, UA by C minimum, UA by C minimum. Okay, this equation you can find the data book page number 161, UA by C minimum, C minimum, MCP minimum. Okay, if MHCpH is greater than that of MCCpC, then MCCpC is minimum. That is NTU is equal to UA by MCCpC. When MHCpH is less than that of MCCpC, so MHCpH is C minimum. So NTU is equal to UA by MHCpH. Okay. Now, in the case of parallel flow heat exchangers. Okay. Recall the temperature profile we use in case of LMTD. The same graph you can use here also. Okay. So, take an elementary area dA and let the heat transfer to that area is dQ. All that is same as LMTD derivation. Okay, so dQ is equal to U dA pH minus Pc, and that should be equal to MH pH dTH. Here, in case of parallel flow, here we have a minus sign, and this quantity is positive MCC dTc, that is equal to minus CH dTH minus CC dTc. Okay, because of the heat transfer, all the fluid is heated up by an amount of dTc, and hot fluid is cooled by an amount of dTH. Okay, so dTH is equal to minus dTH, dTc is equal to CC. Perform the operation dTH minus CC. Up to here, same. It is going same as that of LMTD derivation. Okay, d of TH minus Pc is equal to U dA TH minus Pc. Substitute the value of dQ from this equation. You will get minus U dA TH minus Cc. Then take this towards the left side. You can write d theta by theta equal to minus 2 dA. Okay. Now, here onwards, the derivation has some difference. Okay. So, upon integration, then integrate here. Integration, you will get ln of theta 2 by theta 1 It is equal to minus UA 1 by CH plus 1 by CC. Now you take CH or CC, either one you can take it also. Let's take CH here. Okay, minus UA by CH equal into 1 by 1 plus CH by CC. Okay, left hand side you get ln of, you have ln of pH2 minus pH2 divided by pH1 minus pC1. Let's remove this logarithmic term, so we'll get an exponential term on the right hand side, and put this is equation of equation number 1, pH2 minus pC2 divided by pH2 minus pC1. Now we are going to replace the unknown terms. Okay, we are using this method when both the exit temperatures are unknown, that is pH2 and pC2. pH2 is the exit temperature of hot fluid, pC2 is the exit temperature of cold fluid. So both these are unknown. Okay, so we are going to replace pH2 and pC2 here. Okay, so we know that from the effectiveness equation, effectiveness is equal to this is the effectiveness equation in case of hot fluid, in case of cold fluid, this is the effectiveness equation. I can find an equation for pH2 and pC2. This equation pH2 is equal to pH1 minus this time, and pC2 is equal to pC1 plus, this is plus positive, pC1 plus effectiveness minimum pH1 minus CC. Okay, substitute these two values pH2 and pC2 in equation number 1, rearrange, you will get the equation like this. Okay, 1 by pH1 minus pC1. See, pH2 minus pC2, that is written here, pH2 minus pC2. So pH1 minus pC2 is pH1 minus pC1 here. In equation number 1, denominator you have pH1 minus pC1, and here you have pH1 minus pC1 taken as a 10 here, and minus effectiveness C minimum pH1 minus pC1 is constant for both these terms, minus of effectiveness C minimum pH1 minus pC1, and within bracket you have left is 1 by CH plus 1 by CC. Okay, 1 by CH plus 1 by CC. Okay. So on the right hand side you have exponential of minus UA by CH plus into 1 by 1 plus CH by CC. Okay. Let's take this term within the bracket. You can cancel this term, okay. 1 minus effectiveness minimum 1 by CH plus 1 by CC, that is equal to exponential of minus UA by CH. Okay. Then find the equation for effectiveness by rearranging this equation. Effectiveness is equal to 1 minus exponential of minus UA by CH 1 plus CH by CC divided by denominator you get C minimum 1 by CH plus 1 by CC. Okay. Now consider CC is greater than CH. CC is greater than CH. That means CC is C minimum, CH is minimum, CC is max. Okay. Now you will get the effectiveness equation like this: 1 minus exponential of minus plus 1 plus C minimum by C max. Okay. Change this. Okay. Here you can CH is C minimum, right? If you multiply C minimum in bracket, here 1 plus C minimum plus C max plus C max. If we take the other way, that is if CC is less than CH, and we arrange this equation, you will get the same expression. Okay, here what you can see is take this C max by C minimum outside of the bracket. Okay, so you will get like this. And here Cmax plus C1. Okay, Cmax will cancel. We will get minus. Get the same equation. 1 minus exponential of minus u of x minimum 1 plus C1 plus Cmax divided by 1 plus Cmax. This is the expression for effectiveness in case of parallel flow. Okay, so here the term UA by C minimum is UA by C minimum is NTU, and the term C minimum by C max is called capacity ratio R. Okay, so this is actually the NTU is actually a measure of not effectiveness, measure of the area that is or size of the resistor. Okay, this corrects not effectiveness. This is area, size of the resistor. C minimum by C max is another dimensionless term. It's called the capacity ratio R. So you can rewrite the effectiveness equation for parallel flow, which is equal to 1 minus exponential of minus NTU 1 plus R divided by 1 plus R. Okay, so from this expression we can say that the effectiveness NTU method is used when in this method the expression for effectiveness is found by grouping three dimensionless parameters that are NTU, number of transfer units. Other parameters are, that is, capacity ratio. All these terms are dimensionless terms. Okay, and the last parameter is the flow arrangement, whether it is parallel flow, counter flow, closed flow. Okay, third dimensionless parameter is flow arrangement. So effectiveness NTU method is effectiveness. Okay, we are representing the effectiveness equation by grouping three dimensionless terms. Okay, and the effectiveness NTU method is, as we already said, effectiveness NTU method is used when both the exit temperatures for control fluid are unknown. Okay, two limiting cases for both parallel flow and counter flow effectiveness expressions are effectiveness expression for counter flow heat exchanger. We will see the next slides. Okay, when case 1, when R equal to 0, we already discussed in the LMTD case also. R is equal to 0 is in case of condensers and evaporators. Okay, the expression for all type of heat exchangers, parallel flow, counter flow, and closed flow heat exchangers, you can use this will be your equation. 1 minus exponential of minus. Let's check here. If R is equal to 0, this term will be 1 minus exponential of minus NT divided by 1 plus 0. So 1 minus exponential of minus NT. You can get the same equation if we substitute the value of R equal to 0 in this on the flow also. Okay, so condensers and evaporators, in case condensers and evaporators, 1 fluid remains constant for the distance. So R equal to 0. Okay, 0. So the maximum effectiveness for a parallel flow heat exchanger is 50%, and for counter flow heat exchanger, if it is a condenser or evaporator, will be 100%. Case 2, when R equal to 1, is in case of regenerators. Okay, you get the parallel flow expression as is equal to 1 minus exponential of minus 2 NTU divided by 2. Case of counter flow, you get NTU divided by 1 plus NTU. These two equations you can get from the data book, page number 161. Okay. Now we will derive the expression for effectiveness for a counterflow heat exchanger. Okay, let's take a counterflow heat exchanger. Okay, here also take an elementary area. The heat transfer through that area is Q, and the temperature difference at the elementary area is pH minus Pc. You can write equation dQ is equal to dA pH minus Pc. That should be equal to minus mc pH dpH. That is equal to minus mc cpc dpc because of the opposite flow direction of all the fluids. Okay, opposite flow direction. Flow direction is opposite. Yeah, so both terms here is negative. Okay, same way you follow in the same way as previous derivations. Okay, take dTs, dTc, then d of pH minus Pc, then substitute the value of dQ from this equation here and rearrange the equation, then integrate within the limits area 0 to capital A, and the temperature is equal to outlet point. Okay, so get ln of this term, ln of. Now from this equation you can take Cc or Ch outside of the bracket, so you get Qa by Cc 1 minus Cc by Ch. Now we are going to remove this non term, so you will get pH2 minus Pc1 to pH1 minus Pc2 to exponential of right hand side, you get exponential 10, put this as a percent. Now we have the total effectiveness equation in case of water fluid and water fluid here, and now we are going to replace the unknown terms pH2 and Pc2 from these equations. Okay, so from this equation you write the equation for pH2, that is equal to pH1 minus sketch. From this equation find the equation for Pc2. Okay, that will be Tc2 is equal to Tc1 plus so minimum Cc. Put these values in equation in the previous equation, so you will get like this. Okay, here pH2 is here and Pc2 is on the denominator. Okay, so substitute that values in the equation and rearrange. Okay, so you can take pH1 minus Pc1 outside, see this term and this term pH1 minus Pc1 is there. Here also pH1 minus Pc1, pH1 minus Pc1 is there. Take it outside, you get 1 minus this time. Right hand side does not change. Now assume Cc is less than that of Ch. Okay. In case of parallel flow heat exchanger, we have Ch taken outside. See this from this expression, we taken Ch outside. Okay, I told that you can take either term Cc or Ch outside. So that's why I take here, take Cc. Okay, to understand that. Okay, take either way, Ch or Cc. Okay, so if you take Cc outside, let's give Cc as C minimum, Ch as C max. Okay, so here you can you will get 1 minus effectiveness C max because Cc is C minimum here. Okay, you cancel that one. That is equal to exponential of UA by C minimum C max. Okay, let's rearrange the equations. Multiply this term with the right hand side, so you will get this term minus effectiveness of this term. So, and the effectiveness terms. Group together on right hand side, the main term on the left hand side, that's 1 minus this term on the left hand side, this term take it out to the right hand side and take the effectiveness term outside of the equation and rearrange the equation and find the equation for effectiveness. Get 1 minus exponential of Q is upon C by C max minus this term. Okay, it's fraction of variance minimum minus. Okay. Now you know UA base minimum is NTU and C minimum is max R. So here we will get NTU. Okay, just rearrange it here. Okay, let's take this term first and minus 1. Okay, the same way here also, this term first and this term second. Okay, so you will get effectiveness equation is equal to e raised to NTU into 1 minus R minus 1 divided by e raised to NTU into 1 minus R minus R. Let's rearrange and take it into a standard equation. Okay, so e raised to minus NTU, take e raised to minus NTU 1 minus R outside of the bracket, so take 1 minus 1 by this term. Here also you will get e raised to NTU into 1 minus R multiplied with 1 minus R by e raised to NTU minus R. You can cancel these two terms, get a expression as 1 minus e raised to minus NTU 1 minus R by 1 minus R into e raised to minus NTU into 1 minus R. This equation, standard equation, you can find this equation at page number 61. Here NTU is to be minimum and R is equal to C max. Now these are the equations you can find from the data book. Okay, this is and the same is R. Some textbook follow the observation C for capacity ratio. Some textbook follow capital R for the capacity ratio. So here, for specific values of U and C minimum, we can see the equation for NTU here, U and C minimum, and specific values of U and C minimum. If NTU increases, the area of heat exchanger is also increases. That's why earlier I told that the value of NTU is a measure of the heat transfer area of or heat transfer size of the heat exchanger. Okay, heat transfer surface area or size of the heat exchanger. NTU is a measure of the heat transfer area or the size of the heat exchanger. The larger NTU, the larger the heat exchanger. Okay. Refer data book page numbers 160 to 162 to get the correlations for effectiveness and NTU, and page number 171 to 176 you can find charts for effectiveness and there are some observations. If we draw effectiveness NTU chart for all the type of heat exchangers, crossflow heat exchangers, you can see the first observation is the value of the effectiveness ranges from 0 to 1. Effectiveness of the all the heat exchangers ranges from 0 to 1. It increases rapidly with NTU for small values of exchanger, that is up to NTU is equal to 1.5. You can see from the this graph, you see up to 1.5 value NTU is equal to 1.5 for all type of heat exchangers. The effectiveness value is increases rapidly. Okay, and it will increase slowly for larger values. Okay. For a given NTU and capacity ratio, the counterflow heat exchanger has the highest effectiveness. Always, the counterflow heat exchanger has the highest heat exchanger, and the parallel flow heat exchanger has the lowest heat exchanger. Always, force flow heat exchanger is in between these two, counterflow and parallel flow. The value of the capacity ratio ranges between 0 to 1. For a given NTU, the effectiveness becomes a maximum for R equal to 0. This is the graph showing R is equal to 0 for all exchanger. Okay. Effectiveness becomes a maximum for R equal to 0. That is in case of phase change, and a minimum for R is equal to 1. That is for a high generator. For R is equal to 0, the effectiveness expression reduces to effectiveness is equal to 1 minus expression of minus ND. Okay, so with this I conclude this part of the lecture. The problems of this topic we will discuss in the next part. Thank you all.